All right, in this video, we're going to be working with isosceles and equilateral triangles. Now, with your earlier classes with pre-algebra and algebra 1, I'm certain that you've worked with isosceles triangles and equilateral. I'm certain that the vast majority of the work that we're doing here will be a little bit of a review of things that you've already seen before. However, we do have one proof at the end that's a bit of a challenge, and the proofs are, of course, the piece that we really care about because we're in our proof and explanation unit. Our objective then are to be able to prove a theorem about equilateral and isosceles triangles, as well as applying the properties to solve some problems. Basic vocabulary that you should be familiar with: legs of an isosceles triangle, vertex angle, base, and base angle. These pieces all tie in to the picture of an isosceles triangle pretty quickly. We know that if you have an isosceles triangle, two sides are the same. Well, at least two sides. We do remember that you could have all three sides that are the same length, and that would make it still be isosceles. Well, those two sides that are the same are called the legs. The third side then, the one at the bottom, that's called the base. Sometimes students think the base means it's the one that's on the bottom. That's not the case. We could actually redraw a triangle so that it could be on its side. And in this instance, we would still have our two legs, and the side on the left would be the base. The legs are the congruent sides. The base is the third side. Base angles comes from these two angles that wrap around or kind of trap the base. And of course, if those are the base angles, that leaves the top one to be called a vertex angle. And remember, it's not about the top of the picture, it's the top of the triangle, even if the triangle is kind of tilted on its side. Where these play a role is inside the isosceles triangle theorem, as well as inside the converse of the isosceles triangle theorem. Generally speaking, people don't often remember the name of this stuff. They generally remember just what it says. These are telling us that if you start with an isosceles triangle, so you already know that you have two sides of the same, that would guarantee you that those base angles will be the same. Likewise, if you start by knowing that the base angles are congruent, then you get to end, your conclusion would be that it's actually got two sides that are the same. In general, people remember these things as one combined fact. The isosceles triangle theorem and its converse are usually just stated as the base angles of an isosceles triangle are congruent. Of course, this can play a role with the kinds of problems that we've worked before. For instance, explain why this length has to be yz. And you'll notice I've already got the answer typed up here. What we would have to observe is, since this is 140, we'd be able to create a linear pair that says the other side's 40 as well. Because the both base angles are both 40 degrees, that would guarantee us this is an isosceles triangle. Since it's an isosceles triangle, these two legs are congruent. They have to match in length. We're done. It's got to be 20 feet. Similar, or rather different kind of problem. One type of problem that I'm certain you worked with earlier are ones like this. If you're given the vertex angle, figure out how big the base angle is. Of course, the important characteristic that you're supposed to observe, we are given the fact that this is isosceles, which instantly tells us these two angles are the same. Well, if these angles are just going to be called angle x, they're that can be combined with another very well-known fact about triangles. If you add up the three angles of a triangle, what do they always add up to? We know that they always add up to 180, so we could create an equation saying angle 1 plus angle 2 plus angle 3, their measures will add up to equal 180 degrees. And so we can create equations based on this relationship. When you worked with this before, you probably didn't go and create equations. It's more likely that you were simply taught you can take the 180 and subtract off the vertex angle. When you subtract that, you wind up getting 158. Because the two base angles combined are that 158, we'd be able to simply divide it between those two base angles and get that each one of them has to be 79 degrees. And so there we're done. We've got a 79-degree angle. In your earlier classes, pre-algebra, so forth, middle school, I'm sure that you worked with problems that were like this. Where we build upon them are, we focus on pieces that actually start putting variables in it. We combine that pre-algebra skill with the algebra equations. When you look at this problem, you are supposed to recognize the tick marks. 2 tick marks tells us we have an isosceles triangle. That tells us then that the base angles are congruent. Since the base angles are congruent, that lets us create an equation saying 3x is the same as x plus 44. That's where the geometry play comes into play. Recognizing the relationship, creating the equation. Now we'll kick in and use our algebra skills. Subtracting x tells us 2x equals 44. We can divide out by 2 and get x equals 22. But please note, that's not saying 22 degrees, that's just saying x is the number 22. We would have to put that back in and note that to get the measure of angle G, we can plug in 22 for x. 22 plus 44 gives us our answer of 66 degrees. And we're done. But all of that was based on isosceles triangles, where we know at least 2 sides are the same. That has a very immediate consequence into equilateral triangles. In particular, what we would observe is we are told these 2 sides are the same. That would mean angle B and angle C are the same. Similarly, though, these 2 sides are the same, which forces angles A and C to be the same. Well, what we notice then is because we are given equilateral, it actually forces all 3 angles to be congruent, so we get equiangular also. Anytime you have an equilateral triangle drawn like this, where we know all 3 sides are the same, you get all 3 angles for free. Similarly, it works backwards. Using the converse, because 2 angles are the same, it forces the sides. Because 2 angles are the same, it forces 2 sides. Well, that winds up telling us all 3 sides will be the same. If you have a problem that begins with equiangular, it gives you equilateral. This is the main reason why equiangular is not a very popular vocab word. In general, when you have a picture that has all 3 sides are the same, or all 3 angles the same, a lot of times people just say it's equilateral. If they see this picture, a lot of times we're just told this is equilateral simply because it causes it to be equilateral. Now, naturally, we can have these facts, and we have to consider how we use them. When you look at this problem, our directions say find the value of x, you are supposed to observe that all 3 sides are the same, so we have equilateral. that causes it to be equiangular. All three of these angles then are going to be 2x plus 32. And so we could create an equation, angle 1 plus angle 2 plus angle 3 equals 180. Please remember what we had before. The last time we worked with equiangular, we had the observation that all three angles are the same. So if we have three angles that are the same, angle 1, angle 2, and angle 3 adding up to 180, we observed before that we can simplify that algebra and observe that tells us in an equiangular triangle, where you know all three angles are the same, and now if you know all three sides are the same, it tells you each one of them is 60 degrees. So we could just solve one simpler equation. Subtract off 32, that's 2x, whoa, that's 2x equals 28. And then when we divide out by 2, we get the answer we were searching for. The value of x is 14. We're done. As a related problem, please notice all the angles are congruent, which means all three sides will be congruent also. We can use that as the basis, saying sides are the same, to create our equation. 5y minus 6 equals 4y plus 12. Now we just have to solve it. Subtract off 4y. You get y minus 6 equals 12. Add on 6. And we get y equals 18. And we're done. Now, the last problem with this video is designed in part as a review of some things that we learned back in Unit 1. Prove that the segments joining the midpoints of two sides of an isosceles triangle is equal to half of the base. So, given an isosceles triangle ABC, and I'm just drawing it down here saying, all right, drawing my isosceles triangle, come together and note, here we go. X is the midpoint of AB. Okay, so here's X. Y is the midpoint of AC, right? Indicating that we have legs AB and AC. We want to prove that this distance from X to Y equals half the distance from B to C. And in order to do that, there are several pieces that we need to observe. To start, we are trying to figure out the lengths of X and Y, or rather the length of the segment XY right here. We are trying to figure out the length of this segment BC, which is the base. I'm going to pause here and say before we continue, this is a problem that's hinting at a future theorem. In our next unit, we are going to learn about the Mid-Segment Theorem. With this particular picture, this one here in the middle is actually called a mid-segment. This is again something in our future unit. It's given its name because X was a midpoint, Y was a midpoint, and so it's a segment that connects a pair of midpoints, hence mid-segment. This part down here was our base, and so the statement that the mid-segment is half as long as the base is actually a theorem we're going to work on down the road. This is kind of hinting towards at it right now. Now, in order to actually address this problem, we're going to need some distances. So if we're going to get distances, we are going to have to use the distance formula. Whether you use your notes to look up the formula or you remember it, you will need to use the fact that we can take a pair of x coordinates and square them. We can find our difference between a pair of y coordinates and square them. And this equation, based on the Pythagorean theorem, is how we can get distance in between 2 points. Of course, this presents a challenge. If we're going to use this formula, we have to have coordinates. We actually have to have numbers. To help make this problem a little bit easier to see, I'm going to do this originally with some actual numbers so we can see the process with actual numbers. And then I'm going to replace those numbers with letters. I'll replace them with variables. Our first observation then has to come over here and say point B is the origin, 0, 0. Point C, if we go through and count this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's the point 12, 0. Our point A, 1, 2, 3, 4, 5, 6, 7, 8 up. Again, noting 1, 2, 3, 4, 5, 6. So 6 up and 8. We have all of our points for our isosceles triangle. I would like to observe what we could do. We could use the midpoint formula and get the coordinates for the midpoint x as well as the midpoint y. What we would need to do are take these two pieces and say, using the points A and B, we could take 6 plus 0 over 2, 8 plus 0 over 2, and this formula gives us the coordinates for point x. Simplifying those, 6 plus 0 is 6, 6 divided by 2 gives us 3, 8 plus 0 divided by 2 gives us 4. So we have the coordinates 3, 4 for x. And likewise, we would do the exact same kind of thing for point y. Taking 12 plus 6 over 2. Taking 8 plus 0 over 2. And what we wind up with are the coordinates 8, 4. Now that we've done the midpoint and got the coordinates for all of those points, we can finally come back over to the distance formula and actually crunch in some numbers. The distance from x to y, well, this is one that we really wouldn't want to use the distance formula. It's a perfectly horizontal line. Instead of using the distance formula, we could simply count 1, 2, 3, 4, 5, 6. We can simply count over and say, hang on, that's not 6. We're looking at the distance here from 3 over to 8. So 1, 2, 3, 4, 5. Okay, I see what happened. I had a number crunching error. Down here, we took 12 plus 6. 12 plus 6 is 18. 18 divided by 2 would be equal 9. This isn't the coordinates from 8. That's 9. And it's a good thing that I saw that here before we continued to go further, because that would have caused some problems for us. Sorry for making an arithmetic error. Okay, but still counting it, that was a distance of 6. Likewise, now we need the distance BC. And once again, we're lucky the way that we've got this drawn that we actually don't need the distance formula. From B to C, going right down along the bottom, because it's perfectly horizontal, we'd be able to just go through and count and simply say that's a total of 12. Now with this length of 12, we could then put these two pieces together and observe the distance xy equals half the length of that base. And there's our proof. We're done. By itself, though, this is not a classic proof. Because we use specific numbers, this is an example for one specific problem. This is not a generalized theorem that's true for everything because we did not do it with variables. This is a piece that we will come back to it. We will hit this problem up again in our future unit, and we will there show that it's true for everything. That every mid-segment is equal to half the length of its corresponding base. This is